Hey everyone, we're going to be talking about special atmospheric soundings that you need to know the names of and where they come from, including the really most important one, which is the loaded gun sounding. And we'll be talking about this very cool thing about the EML. So we're going to start out by reminding you that we talked about, oops, I think I need to do this, right? I need to share my screen. We talked about, I think this blocked me last time, some of the words I wrote. I'm going to do this. I'm going to talk about soundings, and this is a sounding just to keep in mind. Okay, we do this, and we do this. And then from here, we're going to draw more than that. So let's say we have a sounding that looks like this. Now this is not the sounding I want to talk about, but I do want to remind you that whenever I have a sounding like this lowest part is the planetary or the convective boundary layer, because it's dry adiabatic, the temperature drops at 10 degrees Celsius per kilometer, and the mixing ratio is for the most part constant. Now, this is what happens during the day, but at night what starts to happen is you get temperatures at the surface start to cool down. So the environment is going to look something like this. I'm going to take this out, and I'm going to say that the temperature of the environment is going to do something like this, where it's still kind of dry adiabatic, but then the temperatures cool down. And as that goes, you may even cool down more than that. So maybe dry adiabatic, and then the temperatures really drop down quite a bit. Now, in this case, what we are saying is that because the temperatures are cooling at night, instead of having a dry adiabatic lapse rate, we now have a temperature inversion. Now, a couple of times I have talked about a subsidence inversion, stable air when air sinks. That's what an inversion might be. But in this case, the reason it is this is happening at nighttime. So when I see the temperatures come down, that's what's called a nocturnal sounding. This is what you would expect to see at night, because the temperatures are going to go. So this is a surface-based temperature inversion. Now, something to keep in mind is, imagine that the temperature drops to the dew point. If the temperature drops to the dew point, maybe something like this, then we're going to have what? What do you think is going to occur down here? I hope you come up with an answer. Some of you may say dew that'll form, but if it's deep enough, it's actually fog. So this is a type of what we call radiation fog, but the temperature simply drops to the dew point. And so we get a surface-based inversion, and we get fog. Now, keep in mind that this is probably going to form when the winds are not going, because if there was wind, what would the sounding look like? Let's do this. If there were wind, the sounding may look like this. It would maybe try to be an inversion for a while, but then maybe right near the ground, there's your mechanically induced turbulent eddies creating a well-mixed boundary layer. Now the dew point, it can do other things. I mean, there's winds going on. It's always going to advect or change maybe, but for the most part, I'm more concerned about the temperature. So this case, this 500 meters or so may be a well-mixed layer, but there's still usually an inversion that will occur. So whenever I see that really stable air at low levels, that is going to be a nocturnal sounding. Now I want to take a look something about a nocturnal sounding. If I were to lift a parcel in a nocturnal sounding, this is where things get kind of weird. So I lift it, the LCL is really close, right? There's your LCL, and so your parcel is going to go up like this. Let's move it this way. Something like this. There's your wet adiabatic. Notice it's stable all the way up. So this is really bad, and that's why we don't look at the lifted index overnight, because we have to interpret what it might be later on during the day, but at night it's going to be stable because the ground has cooled off. Now, in this scenario, that is why we typically use the Showalter index. So let's see how the Showalter index would go. So I'm going to start here, let's say, and go up dry adiabatic, because remember, where does the parcel start? The parcel starts at 850 millibars. And if I go up a mixing ratio line from the dew point here, then I'm going to get something that might look like this. And now my parcel going up wet adiabatic. I'm having trouble hearing you. Siri, relax. Then I get some cape that's going on in here. And if this is 500 millibars, then I would have a negative Showalter index, even though my lifted index was positive. Stable air from the surface, but I have to lift it here. So if I had thunderstorms in a situation like this, surface-based, there'd be nothing, but these would be elevated thunderstorms because there is instability from elevated parcels. So that's one way that I might say a negative value in the Showalter index says, oh, it's unstable if I don't lift it from the ground, but the surface air is that way. So that's a nocturnal sounding. Now, during the day, the temperatures start to come up again. And as the temperatures do go higher and higher and higher, then I start getting that daytime sounding. So this goes away, and all we're left with is a well-mixed layer during the day. Now we're thermally induced turbulinities. Okay, so that's sounding number one. Let's take a look at another sounding. I'm going to go with an easy one right now. So let's say the sounding looks something like this. This is going to be dry adiabatic, and then we have a sounding that's like this. Temperatures are decreasing. It's not really steep lapse rates, which like 10, but the dew point might be something like this. Now notice throughout this entire sounding, the difference between the temperature and the dew point, which is called the dew point depression and indicates the relative humidity, is very high. So this is a close temperature and dew point spread all the way up. This is typical of what we might get in the tropics. So this is what we call a tropical sounding when we look at hurricanes. And a couple things about this is not very steep lapse rates, lots of moisture, maybe the K index would be high, and when we see a sound like this, we're going to be thinking about a lot of rain. So you might get cape. The cape would look something like this, perhaps. There's your LCL, maybe something along these lines, and then your cape is going to be this way. So okay, goes very high. It's all cape, but what can you tell me about the cape? In this case, the cape is what we call thin cape. It's not very wide. So it's unstable, the air will rise, but it's not a very strong updraft. This is not producing a lot of severe, but it could produce a good amount of precipitation, of rainfall, okay? So that's a tropical sounding. So we've had nocturnal and tropical. Let's look at one that maybe looks like this. Let's look at a sounding that might look something like this. Maybe we'll use this for a second. And then maybe and then we come up here, get to the tropopause. The difference here is that the mixing ratio might be something like this, the dew point. Now in this case, this is going to be dominated by very big dew point depressions. So the low level air has low RH, big dew point depressions. And then in this area, there's a pretty good amount of moisture. So in here, maybe up higher, there's some moisture. So soundings would be kind of weird. You could actually have a sounding that goes up pretty high, dry adiabatically, and then from here, you might get a parcel that's going to go up like this. And you get some cape very high in the atmosphere. This sounding is what we call an inverted V. So if you kind of think about this for a second, let me take out the cape. Oh, I want to keep that. I want to get rid of this. Okay. If you kind of take a look at what this is sort of like the letter V right there, but it's upside down. So that's what inverted V. You'll find this out west in the mountains, in the Rocky Mountains. And what happens here is you have some instability, so you get high base storms. You get some cape. But because this air is so dry, you get a lot of what? What will the rain do in that region? It will evaporate, which means you're going to lead to downbursts, microbursts. Rain will evaporate. So if it rains entirely evaporated, then it's going to be called virga. Because I have a storm, I have a high base storm. It rains, and very little of the rain comes down, and then you could have a lightning bolt that comes into a very dry environment. And what's the threat with something like this? The answer is this is what causes fires to start. So you have these out west, California, Nevada, Arizona, New Mexico. You get these high base storms that produce lightning, but it's really dry down low. It doesn't rain much. You get lots of wind, and that is a really favorable fire spread. So that's known as an inverted V sounding, okay? So that's 3 of them. Now let's take a look at another one. I'm going to just kind of give you a little background in this. Imagine that here's the ground, that I have someplace over here that's very warm, and over here, this is cold air. There tends to be a boundary somewhere in this, and it's going to be a front. So what we're basically saying is that this air, this warm air, is coming up, and it's going to go over the frontal boundary. So if the warm air is moving to above it, it's less dense, it goes above cold air. So then the question is, what happens if Bob, there's Bob over here with his John Deere hat and his belt buckle, is standing there and launches a balloon? Well, what would the temperature do? Well, the temperature of the balloon is going to go down, and then it's going to go into warmer air. So the temperature comes up, and then as you go higher, it goes down. Okay, so I'm going to erase this eventually, so I'm going to do it now, just the arrows. Okay, so I've got warm air, and what that means to me is I have a temperature inversion. But this inversion is because I'm going from cold air mass into a warm air mass. So this is a frontal sounding, and the inversion is because I'm going through a front. Now the question is, what happens to the dew point? Well, it's not always the case, but the dew point in cold air masses are usually fairly low, and when I go into a warm air mass or a maritime tropical air mass, the dew point goes up. So what's going to be different from what we call the loaded gun is that this layer here is really not expected to be convectively unstable, because not only does it get warmer with height, but I actually get more water vapor in the air. In this case, surface-based parcels, and I'm just going to draw it in pretty simply here. Surface-based parcels might do this. They'll be stable the whole way up, okay? But What if I lifted a parcel from above this inversion, above the front, in the warm air? Now I have all this cape from a parcel that starts above the front. So I have surface-based air is stable. Again, higher up, maybe the Showalter might see this, maybe not. But this is where we get elevated convection. Okay, that's a frontal sounding. Again, temperatures go up like we see in the loaded gun, which we'll get into. And then the difference is instead of drying out, now we have an increase in the moisture. That's called a frontal sounding. So the last one is the loaded gun sounding. So I'm going to just skip to the chase, and I'm going to say, here's the basics of a loaded gun sounding. So I might have an inversion here, and then over here, I'm going to go like this a little bit. So I'm thinking of it sort of this way. And the dew point, again, very similar. What we've done before is we have a dew point that does something like this, but then above it, it dries out. Okay, so this is your loaded gun sounding. And I'm going to say that in here, there is a stable layer. And for it to be a truly loaded gun sounding, it is still convectively unstable. Okay, so that's this region. We'll call this region 2. Now, region 1 is this air down here. So what can we say of this air? We'd say it's unstable because of the boundary layer. Steep lapse rates. Maybe it goes beyond that, but it's still mostly unstable. It's a pretty unstable air. It's got a lot of moisture. Okay, and what that means is you have a moist air mass. Then you get the stable air sinking. So this, just to keep in mind too, this is a result of sinking air or subsidence. But then region 4, what color should we use? We'll use, let's use this color. Region 4, did I say? I meant region 3. Region 3. So just so you know, this was region 1, 2, 3. Now this has got a region of steep lapse rates. It's also, because the temperature in the dew point depression is big, it's also very dry. So again, we talked about the convective instability. We want dry air above this. So the question is, where does this sounding come from? Now this is really big in what we call Tornado Alley. If I asked you, where do you think most of the tornadoes are? You'd say Nebraska, Kansas, Oklahoma, Texas, right? Those areas. And you get loaded gun soundings from this. Okay, so where does that come from? That's really the question that I want to answer. So once again, loaded gun sounding. I'm going to delete this for a second and go to this map. Okay, this map is a geophysical raised relief map. So right here, we've got, this is sea level. We have an air mass in this. It's called maritime tropical. Maritime means it's from over the water. Tropical means it's warm. And so if I get southeast winds, I get moist advection coming up to the plains. And as it does so, it rises over the terrain. Sometimes you get fog in here. Technically, it's called upslope fog, but if you're a storm chaser, you call it upslop. Now, in this region here, this is a very flat region of Texas Panhandle. This is called the llano, 2 L's, so it's Spanish, estacado, which means staked, like I'm putting in stakes in the ground, plains. So back when the Spanish had come over and they were exploring this area, it was so open, so flat, there was no trees, there was no things to remember by. They get lost. So they put up stakes to remind them where they were. So they would see stakes in these plains so that they knew where they were. Okay, so the very flat region. Now over here in this region, you have, this is known as the Front Range. Of the Rocky Mountains, of the Rockies, which not so high down here, but certainly very high through Colorado. Now, last thing is, over here, this region, part of where the 4 states meet, it's called the Four Corners region. This is a very deserty area. This is called the Colorado Plateau. That's how you spell plateau. The Colorado Plateau. Okay, so, but it's very high up. This is about 1 kilometer to 1.5 kilometers above the ground. So what I want to do is I want to say, well, okay, in this area, what does my sounding look like? High terrain, so it's starting very high. It's got hot and dry. So do you agree it's probably going to be an inverted V-type profile? So an inverted V-type profile is going to be basically steep lapse rates down low and then dry air. Now, if it's inverted V, the moisture comes in, but if not, the moisture is really low and then it's just like this, not much. But do you see that this area here, this color, this area here is the convective boundary layer, which means it's dry adiabatic, steep lapse rates. And that goes from around 850, maybe up to 800 millibars, all the way up to maybe 500 or even higher. So very steep lapse rates. But then I got the Rockies. So what's happening is that this air is going to go this way, and then it's going to go up and over the Rockies before it comes back down. So it will sink a little bit as it comes over the Rockies. And so what that does is the temperatures up here start to get an inversion. Because this air mass, which is hot and dry, will stabilize a little bit in the bottom with an inversion. Now over here, so that would be what the sounding looks like there. What about the sounding over in this region? Well, what happens is this. You tend to get very tropical air mass. So lapse rates that may not be that great, but you get lots of moisture all the way up. Here's your dew point. So a lot of this stuff coming all the way up. Okay? So I get this air moving in from the southeast to here. I get this air coming over. So what I'm expecting to be the case is I may have a jet stream that's going to look something like this. Okay, there's the jet stream. So what I'm saying is I take the air from the Colorado Plateau and it comes over the Rocky Mountains, and now this upper level air sits on top of the moist air that's coming from the Gulf of Mexico. So what I mean is in this region here, and I'm going to go ahead and put this all the way up there just so you see it, and I'm going to say I get the steep lapse rates and a lot of moisture down low. I get this steep lapse rates up in the altitudes of the storm, and then the inversion. And that's marked by dry air. Okay, big differences. And then in between, the air is going to go down rapidly. It's going to get drier, but because it's coming over the mountains and sinking back, I get an inversion. And now there is region 1. Region 1 is from down here. Region 3 is the dry air from the Colorado Plateau. And then region 2 is the subsidence inversion, which is the transition between these things. Okay? That's where the loaded gun comes from. So when all is said and done, where do I get the loaded gun soundings? Well, early in the year, I tend to get it about this area. Maybe it advects across into Missouri, maybe on rare occasions in Illinois. That's usually not the case, but this is my loaded gun sounding. As we go into June or July, I can get that same type of sounding maybe up in the northern plains, the central plains, southern plains. So, but the famous Tornado Alley is considered this region, and this is where I go storm chasing the most. Kansas, Colorado, Oklahoma, Texas, maybe parts of New Mexico. But I want to look at one more thing in here. So I'm going to imagine that I have the cross section of this land. High elevation over here. Then I get to the mountains, and then I come back down flat, and then I come down all the way to the sea level. So I'm basically starting there, and I'm ending up here, and I'm drawing a cross section across this area. So again, high plateau, Rocky Mountains, then I get to the flat Llano Estacado, or the Cap Rock. That's another name for it, the Cap Rock. And then it comes off the Cap Rock in toward the Gulf of Mexico back at sea level. So this is your sea level. When the moisture comes in from sea level, it comes in sort of a wedge like this. So this is all the depth of the moisture. Remember, this is sort of a vertical cross section. So you can hide the map. Now you're thinking this is the vertical cross section. So this is a z-axis. So what if I were putting a balloon here in the deep moisture, or Bob was? Steep lapse rates, then you get to maybe the drier air, whatever. And over here, the moisture now comes back out, right? There you go. That's what's going on in that region. But what if I came here, up on the Cap Rock? I get dry adiabatic, and then I get the inversion, and like this. Here's the dew point. Do you see how narrow this layer is? This is very shallow. So what happens is during the day, if it's clear, it mixes up, and pretty soon I start to get eddies that bring in dry air, and I get rapid drying in this region. That's not good for severe weather. Let me show you what I mean. If I'm standing here, my dew point's high. If I start driving my car to the higher terrain, dew point's still high, maybe 60s. All of a sudden, I go from 60s to here, and all of a sudden the dew point drops. Why? Because that dry air has come over the mountain and come down and spilled across the plains. So I have a strong gradient between moist air and dry air, and that strong gradient is called a dry line. Now, typically speaking, this is what a weather system may look like. This is in chapters 7, 8, 9, 10 of your book that you should have done the reading on. I usually have an area of low pressure, and maybe there's a warm front like this. Then behind it, I'm going to get some sort of a cold front. But over here, this is where I expect to find the dry line, which looks like that, scalloped brown lines. So that's my dry line. And what that means is that here it's warm, moist. Up here on this in the cool sector, it's cooler, drier. Here it's cold and dry. But what's the weather like here? Well, it's coming down, it's compressed over the mountains, so this air is warm and dry. So across this thing called the dry line, from here to there, I could get dew points that might be 20 degrees dew point, and over here could be 65-degree dew point. I've seen it where the dew point drops maybe 30 degrees in a matter of a mile. I mean, you can drive through it and feel the difference. So this becomes a focal point for thunderstorms to convect. There's going to be lift on the dry line. And so a lot of times you get thunderstorms that are going to form over there along the dry line. Okay, so that's where my thunderstorms are going to be forming, somewhere on the dry line. And those are some of your big severe weather. I like this weather here near the front or the triple point. We're not going to get into that on this lecture. We can talk about that during class. But the point being is the dry line is something that we often see. If I mix down the dry air, the dry line can move very rapidly. It probably won't mix out here. So think about eddies that may be this tall, right? Dry air is coming down, but over here, those same eddies are going to be mixing in moist air. So you're not mixing out the air. So always watch for the dew point. If you see the dew point go down, you're mixing out air. Dry air is coming into the boundary layer. If the dew point stays constant, well, that's usually a good sign. So that's going to be where the storms are going to form, and the soundings along the dry line are going to be the loaded gun sounding. Okay? So review 5 types of soundings you need to know. The first one is the nocturnal sounding, which is a surface-based inversion. The second one is going to be an inverted V, which is big dew point depressions down low and more moisture up higher in the atmosphere. You're going to get frontal sounding. You're going to get a tropical sounding. And then this last one will be the loaded gun. The loaded gun is not dangerous all the time. It's potentially dangerous. And as a result, you need some lifting mechanism to break that in. And that we'll talk about hopefully in class. Okay, so that is a look at some soundings. Those are the things you're going to need to know for the test. And we've come full circle with this unit. And this is probably where we're going to leave off as we start looking into the photograph. Okay, guys. So if you have any questions, please go ahead and write them to me. And if not, I will wish you a very good day.